Hello, I'm Dr. Peter Williams, professor with ASU School of Molecular Sciences, and I'm joined by Christina Forbes, who is a postdoctoral research assistant. We're pleased to participate in this important safety course, which will cover the key safety elements when working with solid and liquid pyrophoric materials, and key procedural factors to consider throughout the process. A healthy respect for pyrophoric materials is required, and strict procedural practices must be followed through the use of standard operating procedures. This entry-level course provides ASU researchers key elements for safe handling, storage, use, transportation, and disposal of pyrophoric materials. It will assist with the development of a step-by-step SOP for handling solid and liquid pyrophorics in the laboratory. This course must be supplemented with lab-specific training that reflects how each specific substance is handled in your specific laboratory.
Pyrophoric materials supply the energy for thermodynamically difficult reactions. A reaction that has a high energy transition state or that has products of higher energy than the starting materials may benefit from the use of a pyrophoric reagent.
When I first started conducting chemical research, it was very simplistic in a sense. We used to just take salts and water and heat them together in an oven. But as you go on to make more useful and reactive reagents for synthesis, sometimes you need to use those pyrophorics to create the catalysts that you're interested in making.
That's really the point, isn't it? That no one goes out of their way to deliberately design a project that requires a pyrophoric material. Instead, you learn to use pyrophorics because there is no other way synthetically to do the thing that you're interested in. And so, sort of by virtue of no other choice, you have to take on a material that has some hazards associated with it.
Common applications for pyrophoric materials include metal deposition, polymerization initiator in the production of elastomers, organic synthesis, and various applications in semiconductor manufacturing. A pyrophoric material can be water or air reactive. This means it reacts energetically with either. Pyrophoric substances can ignite spontaneously when exposed to open air. Pyrophoric materials exist in three states of matter: solid, liquid, and gas. Pyrophoric gases will not be discussed in this course. Common pyrophoric liquid materials include alkylithium reagents, boranes, and Grignard reagents. Common pyrophoric solids include alkali metals, finely divided metals, and metal hydrides. The Safety Data Sheet, or SDS, may define the material as a pyrophoric and water reactive. Review all of the SDS sections for hazard information, such as hazard properties, handling, storage, and disposal. This information will serve as a key source of information when developing the SOP. Prior to using any of these materials, a pre-developed SOP and lab-specific training is critical for safe laboratory operation. Improper use of these materials may result in research labs being shut down, fires, damage to equipment, injury, and even death. Handling of pyrophoric materials can be high risk, and steps must be taken to prevent such an out-of-control situation, such as verify additional pyrophoric trained individuals are nearby to provide immediate assistance, create a hazard assessment plan and have it reviewed by an expert user, ensure a proper system design, follow the procedures and warnings in the SOP, and work with an experienced supervisor.
To further clarify the unique properties of a pyrophoric substance, it's important to be aware of the distinctions. There are differences between a flammable solvent and pyrophoric materials. All pyrophorics are flammable, but not all flammables are pyrophoric. Pyrophorics are more dangerous than flammables since they react energetically with air and generate sufficient heat to ignite. A fire extinguisher may not be effective on pyrophorics. Full emergency procedures will be covered later in this course. Unique hazards associated with pyrophoric products include highly energetic, may spontaneously ignite, and react with air or moisture.
It's an important aspect of this. There's a need for pyrophorics as we explore new material space and the use of these materials, but with that comes a respect for these materials as well. And with the appropriate training and use of appropriate equipment and safety precautions, these materials can often be handled without danger or without incident.
Precautions to minimize the hazards include: never work alone. Alert other lab personnel of your pyrophoric use, and confine spills to small, controlled areas. Eliminate the proximity of other fuels that could ignite and therefore feed and spread the fire. Maintain an inert atmosphere, isolation of pyrophoric materials from contacting air. Prevention is key. Perform a hazard assessment and ensure the equipment and workstation setup are correct by doing a pre-check.
Due to the unique hazards associated with pyrophoric materials, lab-specific training is essential and required. The remainder of this course discusses the preparation for safe handling, use, storage, and preparing for potential emergencies.
Because pyrophorics may ignite or react violently on contact with air or water, they must be handled under an inert atmosphere devoid of air or moisture. Pyrophorics are commonly dissolved or immersed in a flammable solvent or oil. Chemicals that spontaneously auto-ignite in air or humid air can be identified using the globally harmonized system hazard code with an H designation, which is assigned to a hazard class to describe the nature and severity of a chemical hazard. Pyrophorics are assigned the code H250, catches fire spontaneously if exposed to air, or H260, in contact with water releases flammable gases which may ignite spontaneously. This can be found in the SDS.
Before you're going to take on any kind of chemical synthesis, but certainly one involving a pyrophoric, you sit down and plan, what is it that I'm doing? What do I do if something goes wrong? So that you have everything ready, assuming the worst case is going to happen.
While it may be tempting to get right to the experiment, additional planning for your reaction is one of the most important steps. Each reagent will have its own behavior and reactivity profile. This plan must be written down in a standard operating procedure, which also includes procedures in case anything goes wrong. The SOP must be reviewed by another doctoral researcher or principal investigator who can critically review your process and plan procedure. It is preferred to use a qualified person outside your lab for full objectivity. The SOP provides specific instructions related to preparation, hazards, emergency procedures, handling, storage, and disposal. Review the relevant SDS and guidance to minimize risks. Use the SDS as a starting point for developing the SOP document. Anyone working in the lab, where the reagents are used and stored, must receive training on the SOP so that they follow approved procedures and react safely in an emergency. Reaction planning requires an understanding of the chemistry being performed. Consult someone who has the required chemistry knowledge and experience to make sure all byproducts and reactivity have been determined. This may require going outside your particular lab or school.
Scale can also be an important factor, especially if gases are released. Gases expand in volume significantly compared to when the atoms are stored in the chemical structure of liquids or solids. If enough information is known about the reagent and its reactivity, calculations as to how much gas comes out of a particular unit of the reagent can be made. The scale of the reaction and the size of the reagent bottles should be kept small enough to reduce the hazards involved. If there is a catastrophic release, the hazards are significantly decreased if the amount of the reagent is small. Therefore, purchase smaller reagent containers.
The scariest fire that I've ever experienced as a researcher was when we were quenching a bottle of methyl lithium. And methyl lithium, when it's exposed to air, it'll burn spontaneously. But it's the solvent that's the problem, right? So when I had this bottle and I opened it, I barely cracked it open. And of course, the remainder of the solvent caught fire, but it was the solvent that was next to it that caused the main scare. So both of your points on being aware of your environment are very important.
Using the least energetic pyrophoric material possible and limiting the concentration of a pyrophoric reagent is also helpful. For example, pure triethyl aluminum reacts explosively with water, but with a 20% solution of triethyl aluminum in heptane is less likely to ignite when quenching with water. Use caution and minimize volumes when handling dilute pyrophorics if they are being stored in flammable solvents, because the solvent may ignite. The ability to handle products and byproducts and the ability to clean up the apparatus can be ensured by performing a reaction quench at the end of the reaction's runtime. A quench is the process of adding an excess of some reagent, usually an oxidizer, that will deactivate every chemical in the reaction apparatus in a gentle and controlled manner. The chemicals and any residue inside the apparatus should no longer react with air before the apparatus is open to air. Even though some reactions will create products that are no longer air or moisture sensitive, there still may be some reactants remaining, and so a quench is still an important safety measure. The reaction can be quenched at any point before the apparatus is open to the air. Any chemicals or portions of the reaction mixture that will later be exposed to air should be quenched prior to exposure. It is possible that even when proper quenching procedures have been followed without incident in the past, it is not a guarantee of future events, as explained in this testimonial.
The thing with pyrophorics is that these materials are so dangerous and unpredictable sometimes that you really have to make sure that you have a good plan in place before you ever start working with them. It doesn't matter how experienced or practiced or ready you think you are, it's always a really good idea to triple check your standard operating procedure and your plan for what's going to happen, because these materials can go very badly very, very quickly. So I had an experience in my lab a few months ago where we were working with a material that we'd been synthesizing for a long time. Worked with it dozens of times and thought our standard procedure was going to be fine to keep everything safe. We'd worked with it outside the box in open to oxygen and nothing bad had happened. But on this particular day, there was the right set of circumstances where it can go wrong, and that's ended up what happening. So what had happened in this day was I was isolating some of the material inside the glove box, and the way we remove some of the solvent from this material is you take the material inside the glass vial, cap it with the vacuum septa that has a Kim wipe inside to prevent any major spills, material getting pulled into the vacuum of such thing. So what happened was when we took that Kim wipe out, there was a small amount of material that had gotten stuck within the Kim wipe, and it was finally dispersed, and now it has a fuel. So as soon as we took it out of the inert atmosphere, out of the glove box into oxygen, it reacted immediately, caught fire, whole Kim wipe burst into flames in my hand, and then from a distance from here to my face, there was a large fireball, burned most of my beard, my eyelashes, my eyebrows, even while still wearing safety glasses, and burned my hand right through the glove. So it just goes to show how dangerous these materials can be, even if it's something that you have a ton of experience working with. There can be the right set of circumstances that makes it go bad. So following these procedures and these incidents, it's important that we go back and look at, well, what was in our operating procedure that didn't prevent this, and how can we change this to prevent it further from happening again. So since then, we've looked at our SOPs, determined where the problem was, and gone back and changed them. And I think it's important that whenever you're working with materials that are super hazardous of this nature, that you're always constantly looking at, how can I prevent accidents from happening, and is what I'm doing now going to be enough to keep yourself and the other people in the lab safe.
Use caution during the quench of any reactions or unused pyrophoric reagent. The quench itself can release too much energy at once, particularly for the highest energy pyrophorics. Steps to avoid fires and explosions during the high-risk quenches include diluting the pyrophoric, performing the quench under an inert atmosphere, placing the reaction vessel in a cold bath, using a series of step-down quenches to more gradually lower the energy of the pyrophoric. Do everything possible to ensure no explosive or unstable compounds are created during or after the reaction. This requires the anticipation of what could happen. Preventing the formation of unstable or explosive compounds requires an understanding of expected reaction intermediates and an investigation of any literature on previously discovered side reactions, related reactions, reactions with the solvent, and reactions with the quench reagents.
When I first started my lab, we did rework existing glove box techniques, SOPs, so that we could handle our materials. But then when we started to think about quenching those materials, I very quickly realized that we needed to have different protocols for the different reagents that we use.
I think it's important, this idea of iterative redesign as well, right? As you write something, you're experienced, you're sitting in your office, it looks good, but then when a student tries to use it, you think, oh, well, he didn't quite do what I intended here. And that's okay. I mean, that's just an opportunity to improve it and make it safer and refine things.
As a review, the four major things that should be accounted for with reaction planning. Energy releases must be slow and controlled enough to be safely contained by the reaction apparatus. Reaction scale and size of the reagent containers must be small enough to reduce the risk to people in the event of a catastrophic release. Products, byproducts, and the reaction apparatus must be safely quenched to avoid reactions with air or moisture. Do not allow the creation of explosive or unstable compounds during or after the reaction.
I think that point of situational awareness, being aware of what's in your environment, having a clean working environment, free of materials that can easily catch fire. Something as simple as being aware of where the fire extinguisher, Class D fire extinguishers, are located.
Spills, drips, and dribbles are anything but routine when it comes to pyrophorics. Glove boxes under inert atmosphere are preferred because they prevent spills from igniting. If a glove box is unavailable, liquid handling can be performed under a controlled atmosphere inside of a fume hood, such as a schlenk line or positive pressure apparatus. Handling outside of a glove box can allow small flames to occur, such as residue on the tip of a needle during liquid handling or removal of a septum from a flask. These flames are usually small enough to burn themselves out in a matter of seconds. This is why it's important to maintain a clear work area of incompatible materials and accessory fuels.
Even like if you are experienced with these dangerous material, we are always emphasize on even for people who practice these techniques, not to do the experiment in absence of anybody in the lab. So presence somebody in the lab, it's important.
Yeah, don't work alone.
Don't work alone.
Any spills resulting in a fire lasting more than a few seconds can be catastrophic, and therefore a planned, immediate, and appropriate response is required. Planning for emergencies will require some knowledge of how the reagent behaves outside of a controlled environment. Everyone who works in the lab will need to be trained on these emergency procedures. The emergency procedures should be clearly described in the process SOP. Appropriate smothering materials to consider include dry sand, MET-LX, soda ash, or other materials that will not create an exothermic reaction with the pyrophoric. These extinguishing agents should be within arm's reach. Do not use water, halon, or carbon dioxide fire extinguishers as they are likely to enhance the flame. An ABC fire extinguisher may be helpful to manage additional expansion of the fire. A Class D fire extinguisher is recommended for combustible solid metal fires. The safety data sheet should be reviewed to determine the appropriate extinguisher or extinguishing agent. If a fire occurs in any space where fire sprinklers exist, leave the lab immediately, as the water deluge will react explosively with other pyrophoric materials. After immediately leaving the lab, use a fire alarm pull station to evacuate the building and call 911. Do not attempt to extinguish, as it will put you in serious danger. There may be enough information available about the reagent and its reactivity to attempt to mitigate or contain the spill. If you are not sure what might happen, you should have a strict evacuation-only policy. When in doubt, get out.
If one of the reagents gets in your eyes, the water on the surface of the eye combined with the additional water that comes from tearing up afterwards will have already caused damage. To prevent further damage, always use the eye wash for a full 15 minutes. Then seek immediate medical attention and notify your supervisor. The safety shower is almost always your best recourse, unless the principal investigator and SOP say otherwise. A pyrophoric substance is reactive enough to react violently with water or sweat, and it can destroy the outer layers of skin and continue to react with bodily tissues or fluids. This is why you must wear the proper personal protection equipment and use appropriate engineering controls.
Personal protective equipment, or PPE, is your last line of defense and must be worn at all times and a part of your SOP. When working with the glove box, the PPE requirements can be evaluated but must be stated in the SOP. When handling pyrophoric materials, the best practice is to wear chemical and flame-resistant gloves. Consult your supervisor, ASU Environmental Health and Safety, or another safety professional for guidance on proper glove selection. The ideal glove is both flame retardant and chemical resistant while still allowing dexterity. Consult the reference section of the SOP for the latest guidance on hand protection. Wear chemical splash goggles and face shield to protect from splash hazards, explosion, or highly exothermic reactions while transporting pyrophoric materials. When handling these materials, a glove box or fume hood sash may take the place of a face shield. A lab coat serves as a barrier to exposure against pyrophoric materials. A shirt and long pants should be made of cotton or other natural fibers. Closed-toed shoes that cover the entire foot are required for all labs. Lab coats made with a fire-resistant material are required. Look for the FR symbol on the lab coat. A lab coat must be completely fastened and cover the full length of your arms.
Surprisingly, you'd think these things are standard from lab to lab, but oftentimes even the equipment that's used, such as a glassware or Schlenk line apparatuses, are often very customized and specialized to that environment or a particular procedure.
There are various equipment setups for safe handling of pyrophoric materials. The two most common are the glove box and the Schlenk line. Inert atmosphere glove boxes are an excellent device for safe handling of pyrophoric or water-reactive liquid and solid materials, and are recommended for larger volumes over 15 milliliters. Verify that all materials in the glove box, including the gloves and the pump system, are compatible with the pyrophoric material. The inert gas used must also be compatible with the pyrophoric material. For example, lithium metal has been known to react with nitrogen gas and must be handled under argon instead. When preparing to work in the glove box, there are several safety steps to follow when setting up the workstation. Review and follow the lab's SOP prior to setup for PPE and lab-specific requirements. Remove all flammable and combustible materials from the area, particularly near the antechamber. If you have a quenching location outside the glove box, remove all unnecessary materials and ensure a short, clear path to the quench location. Verify that all materials needed to respond to a spill are available. Check gloves for leaks by inspecting the thumb and forefinger by stretching and observing with a close visual inspection. Repair and replace as needed. Verify the condition of the atmosphere in the box by checking the equipped sensors or by some other means per your SOP to ensure the absence of oxygen and/or water vapor in case a small amount of an air-reactive reagent remains. Upon completion of these steps, the glove box is now ready for use.
Ensure that all users are properly trained on how to get items into and out of the glove box safely, without compromising the integrity of any containers during pressure changes in the antechamber. Even though the atmosphere is inert, all spills must be cleaned up immediately and thoroughly and placed in a sealed container. Debris or residue will collect over time, so regularly sweep up the base of the box and treat as a pyrophoric. Properly remove, quench, and dispose of the material following your lab's written SOP.
Ensure all containers are labeled and sealed with electrical tape or paraffin. Unexpected system failures may occur, so it is important to ensure that all containers can tolerate oxygen or moisture when not in use.
I like to remind people that hazards don't end with the experiment. Always think about how you're going to clean up.
quenching.
Yeah, quenching is a big issue that needs to be addressed.
That's
certainly.
That's
And
why. Yeah.
You'd certainly want people around during that process because, in some cases you may have to think on your feet to prevent yourself from getting into danger.
Transfer the sealed container from the antechamber to the nearby quenching area in your fume hood. Quenching is required to render the pyrophoric material to an inert state. Quenching should be done in a crystallization dish to reduce the amount of flammable gas in the open workspace. Dispose the quenched materials using proper hazardous waste procedures. In this example, toluene is added to dilute significantly, followed by isopropanol dropwise to quench the material. In some circumstances, this can be done in an ice bath. Water is the last step of the quench. This process can be time-consuming. Plan ahead and allow plenty of time. The glove box manufacturer's guidance and the SOP provide general instructions for periodic maintenance of the glove box and supporting systems, such as glove replacement and vacuum pump maintenance. Make sure that procedures, including regular maintenance, are followed. While glove bags provide an inert atmosphere and have been used for handling solid pyrophorics, many glove bag materials are incompatible with reaction solvents and liquid pyrophorics. Therefore, we recommend the use of a glove box for greater protection. If you still plan to use a glove bag for liquid or solid pyrophorics, it must be used inside of a fume hood. Consult the principal investigator and ASU Environmental Health and Safety for more information.